Hello and welcome to the lecture. So in this lecture, we're looking at these so-called trust region methods. And if you're following in the type notes, it's chapters 7 to 8. So there are a number of different approaches to solving the fundamental problem in continuous optimization. And one of the approaches we've been looking at so far is the line search approach. So within that, we had steepest descent, we had Newton, and we had quasi-Newton. And for these methods to work, we really always require that the Hessian should be positive definite. Okay, you expect the Hessian is positive definite at the minimizer, but in general, the Hessian depends on X, and you could be going through regions of the parameter space before you hit the minimizer where the Hessian is not positive definite. And in those instances, the line search methods would not work very well. So there are other methods that do work in such a scenario. And one class of such methods is the trust region methods. So that's what we're talking about here today. So yeah, again, just to recap the rationale, I've given these line search methods. At each iteration, the optimization problem is reduced to a 1D subproblem where we find the step size alpha k by minimizing over all positive alpha. We minimize the one-dimensional subproblem f at xk plus alpha pk. So just minimizing over the one-dimensional parameter alpha. And yes, the level set methods are, sorry, different part of computational math. The line search methods work well when the Hessian is positive definite everywhere. The trust region methods are more robust and they can be tweaked so that they converge even when the Hessian is not always positive definite. So the idea is given here that we're at some iteration xk. And so in the neighborhood of this iteration, our x would be xk plus p. So in other words, we're exploring the cost function in a neighborhood of xk by looking at general points x that are made up of xk plus a small deviation p. So then f at x is f at xk plus p. And the idea now is that we approximate f at xk plus p by a quadratic function. So f at xk plus p is approximately equal to f at xk plus a linear part and a quadratic part. So this is an approximation, and we don't say anything yet about G, the vector G, and the matrix B, other than that these are the building blocks of the approximation, and we call the approximation MK of P. So MK of P is our approximation to f of x, and this approximation is called equation 1. So in a kind of standard Taylor series type expansion or approximation, G would indeed be the gradient and B would indeed be the Hessian. But this in equation 1 is a fairly abstract approximation. So G and B can be anything. Um, they form a generic quadratic approximation of the cost function. And the next step is to introduce a trust region where MK of P is a good approximation to F. So in other words, the trust region, the set of all P, such that the L2 norm of P is less than or equal to delta, is the region where we have trust that MK of P is a good approximation to F. Hence the terminology. So you need some way of defining or describing the size of this trust region. You know, what is the size of this region in which we trust that MK of P is a good approximation to F? But once we've established the size of the trust region, so once we've set delta, we can then solve the model problem because MK of P really is the quadratic model problem. So we can solve for PK by minimizing the model problem. And we just have to be careful now because this is a constrained minimization because we're constraining P to be in the trust region. So this equation 3 really is a constrained minimization. So now it comes down to finding a criterion for establishing the right size of the trust region. And to do this, it's very simple. We look at f at xk minus f at xk plus pk. And we want this to be positive because if it's positive, then f at xk is less than f at xk plus pk. Sorry, just get that right. So if this is positive, then the inequality is the other way around. And then we really are reducing the cost function in going from one iteration to the next. So we want this to be positive to reduce the cost function. Furthermore, mk of 0 minus mk of pk is guaranteed to be positive because pk is now the minimizer. So mk of 0 is guaranteed to be greater than mk of pk because pk is the minimizer. So we have something that we want to be positive and we have something that is guaranteed to be positive. So we introduce their ratio rho k. And again, we want the numerator, the upstairs, to be positive, whereas the denominator, the downstairs, is guaranteed to be positive. So we build our criterion for the size of the trust region on this ratio rho k. So if rho k is positive, then this is good because we're reducing the cost function at each iteration. And furthermore, if rho k is close to 1, then the ratio between the actual decrease and the model decrease is close to 1. So using the model to describe the actual function is a good approximation. So the size of the trust region is good, and indeed we can even expand it at the next iteration. Whereas if rho k is positive, but significantly smaller than 1, then we're not so sure that the model problem is approximating the true cost function very well, and we should leave the trust region, the size of the trust region as it is for the next iteration. Finally, if rho k is negative, less than 0, or if it's positive but much smaller than 1, then either we're not decreasing the cost function, or mk is a very poor approximation of the cost function, in which case the trust region is too large. And we need to reduce it at the next iteration. So this is our criterion for defining the trust region at iteration k. And this brings us to algorithm number 5 in the type notes for determining the size of the trust region. So the idea is we have some maximum trust region delta hat, and we never let the trust region go beyond this. And some initial guess for the size of the trust region. And then we have some parameter eta between 0 and a quarter, and this gives us a criterion for accepting a proposed descent direction. And then we have a loop, so an iterative loop, where we iterate over k, as usual. And in the first step, we find the descent direction by approximately solving equation 7.3, which is the step where we minimize the model problem, doing the constrained minimization. So that gives us pk. Once we have pk, we can calculate rho k, and this gives us our criterion. So referring back to the bulleted list, we have some different scenarios to look at, and the scenarios can be imposed by some condition. So for example, if rho k is less than a quarter, then I'm not approximating the true cost function very well with the model, or rho k is negative, and I'm failing to decrease the cost function. In either case, this is bad. The trust region is too large, and my approximation is not reliable. So I have to reduce the trust region at the next iteration. Otherwise, this criterion is false, so we're okay. And we look at two distinct sub-scenarios then. If rho k is positive and pretty large, and furthermore, if pk2 is equal to delta k, then we're doing okay. Our model problem is is a good approximation to the true cost function. And at the next iteration, I should expand the trust region. Otherwise, I keep the trust region the same. So this here is, if you like, step 1 in the algorithm. And this is where I look into either expanding or contracting the trust region or the trust region boundary. That's step 1. And then in step 2, I have to decide whether or not to accept the proposed change in the guess for the minimizer. So if rho k is close to 1, then I'm reducing. Sorry, if rho k is positive and indeed sufficiently positive, then I'm reducing the cost function by adding pk. So I should accept this change. Otherwise, I reject the change. So the second step here is deciding whether or not I accept the proposed update in the iterate xk. So this is algorithm number 5. I don't propose to go into this in any more detail. There's a model code given in the repository, and you can use that as you wish. Okay, so now I want to talk a little bit about the constrained model problem, which we need to solve at every iteration k. So at every iteration k, we approximate f at xk plus p as mk of p, which is given here. It's a term that's linear in p and quadratic in p. And we need to find the minimizer of the model problem, but we need to be careful now because, okay, I'm minimizing as before. We've minimized the model problem before, the quadratic model problem, but now there's a constraint. It's a constrained minimization that the L2 norm of p should be less than or equal to delta. In other words, the minimizer should be within our trust region. And there's a theorem that tells us that this minimizer exists. It says let B be a symmetric matrix. That's always guaranteed. And it says P star is a global solution of the trust region model problem, so equation 4. So a global minimizer. In other words, P star minimizes MK of P, satisfying the constraint if and only if P star is feasible, obviously, so it satisfies the constraint. P star is feasible. And furthermore, if there exists a lambda positive or 0, such that B plus lambda times the identity times P star is equal to minus G, and lambda times delta minus the L2 norm of P star is 0. So either lambda is 0 or delta is equal to the L2 norm of P star, or both in a degenerate case. And furthermore, that B plus lambda times the identity is positive semi-definite. So the model problem has a solution if and only if these criteria are met. And indeed, these criteria then give a possibility for developing a numerical algorithm to find P star. And that's something that is discussed in the notes. But this is overkill. So you'll remember back to when we were looking at the step size for line search methods. And we said you pick a descent direction using some method, and then the step size is obtained by solving a one-dimensional subproblem. And I said in practice, solving the one-dimensional subproblem is overkill. All you need to do is to find an alpha that satisfies the strong Wolf conditions. So it's quite similar here, that solving P star using this theorem is overkill. And instead, it suffices to find an approximate solution to the constrained model problem. And that's what we do next. The simplest possible way of finding an approximate solution to the constrained model problem is to find a Cauchy point. And draw your attention to that. And the idea behind the Cauchy point calculation is to suppose that delta, the size of the trust region, is very small. Then the quadratic model problem can be approximated even further as a linear problem, keeping P inside the very small trust region. And the P that minimizes this further approximated cost function is the steepest descent direction. That's kind of straightforward. So P should be proportional to minus G. And so a guess, an obvious guess for P, so both the magnitude and the direction now, would put P obviously in the direction minus G, but on the boundary of the thrust region. So my guess, or my P temp, is in the direction of minus G and is such that P temp is delta. So I'm on the boundary of the thrust region. So that's our first guess. But a more refined guess then is to say that P is along the direction of steepest descent, but it's a scaled version of P temp. And the scaling parameter tau is between 0 and 1. And we then determine the optimal value of tau by minimizing this restricted version of the model subproblem. So now minimizing over tau. So we find the minimum value of tau by solving equation 5, and that gives us an expression for P. So let's call it P star. And this is the Cauchy point. So this equation 5 that we now minimize, it can be expanded out. And it's quadratic in tau. And we now have to minimize mk over tau, but always making sure that tau times P temp stays in the thrust region. So this is now a one-dimensional minimization problem, but it's constrained because we want to keep tau times P temp in the thrust region. So the next step is to solve for tau, and we will look at this in a follow-on lecture.